Next speaker will be Tommaso Taddei from Inria Bordeaux, and we'll talk about a discretize-then-map approach for the treatment of parameterized geometries in model order reduction. So, this Tommaso, go ahead.
Thank you very much. Okay, I think I realized that I can share stuff. Okay. Could you see my screen?
Yes, we can.
It's great. So thank you very much, Angela, for the kind introduction, and thanks, Angelo and Lynn, for organizing this event. I should say that this is a joint work with Dr. Lei Zhang from Bordeaux, and it's also in collaboration with Andrea Ferrero and Angelo Iollo. I also would like to thank these other researchers with whom I had several fruitful discussions throughout the years concerning the subject of this talk. So this is probably something that everybody knows here, but I just wanted to say that the goal of parameterized model reduction, PMOR, is to reduce the marginal costs associated with the solution to parameterized problems, where marginal means in the limit of many queries. Parameterized model reduction is motivated by real-time and many query problems and naturally certainty quantification optimal control. In this talk, I will focus on the treatment of parameterized geometries in projection-based model reduction. I think this is let's say, a very important subject and has been the subject of many, many works in the past in the model reduction community. I denote by mu here a vector of parameters. I denote by omega mu a family of parametric domains. And denote by u of mu the solution field which is defined over the parametric dependent domain omega mu. So in order to apply model reduction to this class of problems, we need to recast the problem in a parameter independent domain, which is denoted by omega. To do so, we introduce a mapping phi that is invertible, and such that omega mu is equal to phi mu of omega for all values of the parameter in the parameter range curly p. Sorry, Angelo is requiring to annotate.
No, sorry, Tommaso. I'm just playing with the buttons here to see what happens.
Oh, I see. We want to leave the meeting, I guess, no?
No, sorry.
One moment. I think I should. Sorry. Okay, so sorry about that. So the first task is to actually build this mapping. And to do so, we can use radial basis function, freeform deformation, and many other techniques. The second task is how to solve the problem in the mapped domain for U compose phi. So in this talk, I will only focus on this second task, and more precisely, we'll consider two different paradigms to deal with geometry variations. Then I will briefly talk about projection-based model reduction. Then I will discuss the application to a 2D runs problem, which is a simplified case concerning, but to some extent, that has shared some similarities with the test case presented in the previous talk. So some notation, I denote by curly T a finite element mesh with nodes xj and connectivity matrix capital T, and I introduce the associated continuous or discontinuous finite element space curly X. Given an element W in curly X, we denote by W bold a vector in Rn, which is the corresponding finite element vector value representation of the field W. Given a mapping phi, we can introduce the mapped mesh, phi of curly T, which share the same connectivity matrix with the original mesh, but now as deformed nodes. We say that phi is bijective with respect to the mesh curly T if all the element mapping, so the mapping from the master element to the kth element of the deformed mesh, are all invertible. Note that this is an independent condition compared to the bijectivity of phi, in the sense that it is neither sufficient nor necessary for the bijectivity. Okay, there are really two independent conditions. So in order to explain the kind of two different approaches to deal with geometry parametrization, I first introduce what I call here map then discretize approach. So we consider a diffusion, advection diffusion problem. with the homogeneous Dirichlet boundary condition. We assume that we consider a mapping phi that is Lipschitz, and then it's easy to verify that U compose phi solves the following problem, which is exactly of the same form as the original problem, but with different coefficients. So the idea of what I call here mapped and discretized approach is to first derive a mapped problem, and then devise finite element or in general high fidelity discretization and then model reduction procedures for the mapped problem itself. So to my knowledge, this is the first approach that has been considered. There are several works here show that I kind of recommend, and that consider this type of idea. Okay. Another idea is the following. So we first introduce a mesh of omega. Then, given a value of the parameter, we define the mapped mesh phi of curly t, and we approximate the problem in this way, where we see that now Rk here is the residual associated with the kth element of the mesh, and it's defined over a domain that depends on the parameter. So you see here that in this approach, the PD model is unchanged, but now we deform the mesh. Note that now we cannot really apply model reduction in a functional sense, in the sense that functions here are defined over a parameter-dependent domain. So we need to apply it, and we need to think about this in an algebraic sense. Because since we don't change topology, we can still talk about finite element or finite volume vectors. So from now on, what I'm going to do is to make some comments about the difference and the similarities between the two different approaches. So first of all, the DTM approach, discretize-then-map, involves evaluation of the mapping at mesh nodes. Basically, what we need is to compute the elemental mapping from the master element to the kth element of the deformed mesh. On the other hand, the mapped and discretized approach requires the evaluation of the mapping and its derivatives at quadrature points. And the reason for that is that the PDE model that we have now depends explicitly on the gradient of phi. Okay. The first observation one has to make is that if phi compose psi are all polynomials of a certain degree, then the two approaches are equivalent. Really, two ways of writing the same thing. Another comment that is important is that the discretized-then-map approach may fail for large deformations, in the sense that we need to enforce the discrete bijectivity of the mapping. We don't just need the fact that phi is a bijection in omega. In order to have further insights about the difference between the approach, two different approaches, consider the following 1D problem. So it's minus Laplacian of u equal to sine of x in 0, 1. Consider the following piecewise linear map in 0, 1. And then try and define a mesh which is a uniform grid with NE elements of degree 3. Okay, so we use polynomials of order 3. Then we apply mapped and discretize, the black curve, isoparametric discretize-then-map, which means that we consider the same polynomial order to define the deformation of the elemental mapping, and with the same polynomial that we use for finite element discretization. And then subparametric discretize-then-mapping, which we use a polynomial order of degree 1 for the mapping in each element. So a few comments. So first of all, mapped and discretized fails to recover optimal rate. And this is to be expected because, first of all, we are not trying to approximate U here, but we are trying to approximate U compose phi, which in this case is just Lipschitz. The other comment is that since we have to do Gaussian quadrature rule in each element to actually approximate the integrals, here the gradient of phi is discontinuous, and so Gaussian quadrature rule introduce some error associated with the integration. Another issue is that the discretized-then-map here might have inverted elements. And this explains this kind of noisy behavior. Because for some values of n, we actually have one inverted element where the mapping has a jump discontinuity in the derivative. Okay. On the other hand, in 1D, the discretize-then-map with polynomials of degree 1 is guaranteed to have to be bijective, and so we recover optimal rate, which in this case is order 4. Another comment concerns simplicity of implementation. To explain this, consider an SUPG stabilization of the advection term, which for the advection diffusion problem that we have looks like this. If now we consider the first term, if now we do a change of variable formula, we obtain this identity. So the point I would like to emphasize here is that, first of all, the implementation of the mapped and discretized approach likely requires new assembly routines. Even if you have implemented SUPG, you might not have implemented something like this. The other point I would like to make is that this is really prone to errors and it's very difficult to implement. Even more than that, if you use a mapping which is not twice differentiable, this identity is it cannot even be evaluated. Okay? And this, of course, is an issue. One more comment concerns hyperreduction. So consider a problem which can be written in this form. The boundary term, if you want, but several problems can certainly be written in this form, including, let's say, Iran's or others. Okay, so in this case, you basically have two kind of classes of methods for hyperreduction. One relies on the construction of an affine approximation of the integrand eta. So we try to approximate eta in this way. And then we consider a surrogate model of this type. EIM, GAPPPOD are the typical techniques that are being used in the literature to find this type of approximation. Another class of hyperreduction methods relies on the introduction of reduced integration domain. Basically, instead of integrating over all elements of the mesh, we integrate over a subset of these elements. So the message here is that the mapped and discretized approach can cope with both hyperreduction paradigms. On the other hand, the discretize-then-map requires the introduction of reduced integration domain to avoid integration over the parameter-dependent domain omega mu. That needs to be done online in a sense. In this work, we use element-wise empirical quadrature for hyperreduction. And I should say, but I will comment this later on, that application of empirical quadrature is quite straightforward in the DTM framework. So let me very briefly talk about projection-based model reduction. And so in this work, we use LSPG with empirical quadrature. So basically, we introduce reduced ordered basis Z and Y. We introduce a weighted residual, which reads like that, where these weights are mostly 0. And then we consider empirical quadrature LSPG, which reads this way. Okay? So there are basically several elements that need to be addressed. So first of all, the choice of the trial reduced ordered basis. Here, not surprisingly, we use POD. The choice of the test space, which should be a stability maximizing concept in a sense. And also the choice of this weighting norm. Finally, the choice of the empirical quadrature weights, which, as I said, should be mostly 0. So I should say that you can find all the choices that we made in our work in this paper, but in general, these are topics of active research, in a sense. So what I would like to do now is to explain how to actually implement this, and at least in a finite element context. So just a bit of notation, phi ik finite element is the finite element basis in the kth element of the mesh, and it is the number of degrees of freedom in the kth element of the mesh. E1, ED are the canonical basis. D is the number of equations. So basically, how finite element code works is that you loop over the elements of the mesh. You compute an assembled residual, which is the contribution of the residual associated with the kth element of the mesh. And then once you have this unassembled residual, you assemble this. And this step is independent of the PD model that you use. So basically, what I would like to emphasize here is that computation of this guy relies on element-wise assembly routines that take as input the information concerning the nodes of the mesh in the kth element. Then the assembly of the finite element vectors already mentioned is independent of the PDE. So now you want to implement the model reduction routine associated with that. So again, just a little bit of notation. Y is the test space. T here is the index of the ith node of the kth element. And this is the unassembled test space. And F is the reduced residual, which is basically the evaluation of the variational form in the jth basis of the test space. Okay. So the point is that we first loop over the sample elements. Okay. And then we use this identity, which certainly looks complicated, but is independent of the PD model that we are using. So the message I would like to emphasize here is that this routine is the same routine that we use for finite element calculations. So we don't have to implement anything new. So the model reduction assembly exploits available finite element routines. The second observation is that geometry variations don't really influence model reduction assembly because this routine takes as input the nodes of the deformed mesh. So we just have to deform the nodes of the sample elements to actually evaluate this residual. So very briefly, I would like to conclude by presenting some numerical results. As I mentioned, we consider an Hammett body problem. We use Pallard-Talmaras stabilized P2 finite element, Reynolds 3000, which is quite low compared to the example that had been shown by Carsten and Marcus. And angle of attack is from 5 degrees to 50 degrees. This is one snapshot of the horizontal velocity, and these are slices of the horizontal velocity at x1 equal to 1.1, which is more or less here. So we consider a piecewise bilinear mapping. So basically, this map is the identity 1, 2, 3, 7, and 6, and is a bilinear polynomial in 4 and 5. Okay, I would claim that this is one of the simplest way of describing this deformation. And then this is the mesh that we use. I would like to emphasize that the finite element mesh is not conforming with the coarse grain partition. As a result, we cannot really use the mapping discretize approach because the deformation that we use is not twice differentiable. Here are the results. So just to explain, the black line is the projection, so it's the best that we can do. And the blue line is the reduced-ordered model with some empirical quadrature associated with the tolerance 10-10, and which basically is around samples 0.5% of the total elements of the mesh that we're using. So, but the point here is that we are quite close to the best that we can do in terms of relative error on a 10 out of sample configurations. So just to conclude, we discussed in this talk the treatment of parameterized geometries in projection-based model reduction, and I consider two different approaches: discretize-then-map and map-discretize. I don't claim that I invented any of the two. The kind of takeaways of these studies is that DTM is significantly simpler to implement and can be used in combination with no-smooth mappings, which I believe is an interesting feature. On the other hand, map and discretize can cope with a broader class of hyper reduction methods, and this might possibly lead to larger speedups when these other class of methods make sense, and does not require discrete bijectivity with respect to the mesh. With that being said, thank you for your attention, and if you're interested you can find more information in these two papers and also on my webpage.
Thanks a lot for Tommaso for this very insightful contribution. Are there any questions? Angelo, I see you.
Yes, it's a very fast question. So Tommaso, the red curve that you showed in your results, so that's the standard projection, is that correct?
Red curve, this one?
Yeah.
No, here, essentially, if you use a tolerance that is too high, here 10-6.
Oh, I see, sorry.
Empirical quadrature messes up stuff, and the reduced residual is...
I see. Okay, so my question is the following. What happens if you don't, so you keep all the machinery without the mapping, so you have identity mapping all over the place in terms of error as compared to what you see here?
I mean, if you don't have a mapping, you cannot deform. So basically,
let me say like this. So if you have only geometrical mapping, so is this only geometrical, or you are it's only geometrical?
Yes.
Okay, fine. That's it. So I didn't get it. Thanks.
No, but you're right. So basically, you can. So it's quite transparent with respect to the choice of the mapping that you use. You can think about using better maps.
Yeah. So that's what I thought, that you were using. But since you didn't talk about it, so it makes sense that you didn't use it. Okay. Thanks.
Very poor choice map.
Okay.
Tommaso, in your opinion, in order to extend these approaches to more complex geometries, what will be the challenges?
So I would say, in terms of, let's put it this way. So in terms of geometry, this is quite transparent in the sense that, so the difficulty is how to find the mapping. But once you have the mapping, you can deal with any geometry.
Okay.
So, of course, there is the question of how to find a good geometry transformation. But let's say in terms of implementation, this takes as input the form nodes. So you only need to be able to evaluate your mapping in the sample elements. So no, from this perspective, it's easy. Of course, the difficulty is how to find an efficient mapping.
Okay, thanks.
So I have another quick question, if I may. So it's so would you say that this machinery beyond the finite element framework could be also used for ALE in general? Whatever is the scheme that you prefer?
Yeah, so I mean, personally, I mean, I use CGDG, so continuous Galerkin, discontinuous Galerkin. The difference is that basically here you do two loops, one loop over elements, one loop over faces. If you use this in the finite volume context, you basically need a loop over faces as well. But it does not really change. I mean, let's say you need two routines. One routine that does your let's say your Riemann solver in a sense, or approximate Riemann solver, and one routine that does calculations inside the element. But if you have these two, and if you have the finite volume code, you have these two, so in principle you can use them. That's the advantage compared to the map and discretize.
Thank you.